Good afternoon.
I like your shirt.
Oh, thank you. I actually have a hat that goes with it too, that looks like a baseball cap. All right, so there's, hey, how's it going? You ready to learn some calculus in Hopi today?
Yeah. No, I'm just kidding.
All right.
Not for 189.
You guys, you can just hang around and get extra math.
I'm
Expand your brain.
struggling in 189.
Oh. So there's Jada. All right, so we're good to go. So first of all, Jada, thanks for the email. I had actually was looking for that email that you said that you'd sent me that told me what lessons to or what quizzes to open. And I couldn't find it. So yesterday I was going to ask you to resend it, and then you weren't here, but you resent it anyway. So awesome. So I'll be working on that this afternoon and tomorrow morning.
Okay, thank you.
Okay, so any questions or concerns before we get started? All right, so again, after spring break, on Monday and Tuesday, Professor Blake is going to be subbing for me. And but I told him that I just showed him what we had left. And I said, you can teach anything you want. So I kind of don't know if he's going to pick it up from where we left off or if he's going to jump around. So we'll figure it out, though. But I want him to be comfortable with it. But he said he hadn't taught Calc 2 for about 5 years, so we'll see. I did want to show you one cool thing. Today, they're honoring Olga Ladohinskaya's 97th birthday. I don't know if you can tell this. This is on just Google. But this formula that she has, this is actually a calculus from Calculus 3. Okay. We don't study this in particular, but all these symbols and what's going on here, you will actually understand what this is talking about. So I thought that was kind of cool. But anyway, let's see. So this afternoon and tomorrow morning, basically I'm going to try, I've got to get caught up on the quizzes and the videos. I want to have everything ready for you. So yesterday's video should be posted any moment now. So by the time class is over, you should have that, and that should be kind of, as far as helping you prepare for the midterm. Okay? All right. All right. So, unless somebody has a question before we get started, any comments, concerns? Okay. So today we're going to start in on chapter 9. Now, if you're worried about the timing or whatever, because we were a little rushed at the very end of Calc 1. It's not like that here. Chapters 7 and 8 are really the meat of Calc 2, what we've kind of gone through, and then the rest of it is going to be. It's important stuff, but it's not like it's going to take us, it's not like we're in trouble with the timing or whatever. Chapter 9 is, in fact, it's called First Order Differential Equations. And it's really like the first chapter in possibly the next class that you might take. Because, see, right now we're taking Math 231, Calc 2. And then depending on your major, you might have to take Calc 3, Math 241, or differential equations. Now, I'm pretty sure in physics, Weston, you probably have to take both of them. All right. Let's see, Tobias, what you're going in engineering? Is that right?
No, I wanted to be a surgeon.
Surgeon. Surgeon. You might not be required to take either of those then. Okay. Yeah, from what I remember, well, okay, I guess I should be a little careful. It depends on what area. Like, let's say if for your pre-med you take chemistry, you take heavy in chemistry, then you'll probably have to take Calc 3. So it just really depends on. So that's probably something actually you're going to want to look up pretty quickly, because I am going to be teaching Calc 3 over the summer. And if you do have to take it, I would highly recommend you take it just to be done with it. Okay. I know your sister was glad that she took it. She told me she was happy, and she was like a rock star in there. I think she actually did better, and you can ask her, but I think she actually did better in Calc 3 than she did in Calc 2. So you never know. And it was just a different, skill set. But
I'm actually planning on taking Calc 3.
Yeah.
Even if I don't want to take it.
Yeah. So, yeah, it'll be good. And then, Jada, what are you majoring in?
The engineering.
Engineering. So you're probably, well, depending on you're going to have to take at least one of these. Okay? So you'll have to take one of these. So, anyway, like I say, we haven't offered differential equations at MPC for probably 5 years. I would love to teach it, but right now we've had like 8 to 10 sign up for Calc 3 over the summer between the talent classes and then my Holbrook morning class. I get some over there too. So we've been able to keep that up. So anyway, I hope that works out. But differential equations is kind of another, like I said, this chapter that we're going to do is kind of like the first chapter in the differential equations. There's some aspects of it that I think are easier than regular calculus. Some aspects I think are harder. It just really depends on how it's taught and what the requirements are. I actually, when I took differential equations, and this is not to exclude you, Jada, but this is specifically, this little story is Tobias and Weston. I know you guys were talking about serving missions, right? Right. So this one, and Jada, you can relate to this too. But I was taking differential equations. Let's see. I guess it would be the fall after my. Let's see. No, it was the spring. Maybe it was the spring. So my freshman year in college. So I'm taking differential equations, and I actually have 100% average going into the midterm. And the night before the midterm, I got my mission call. All right. And so when I should have been studying for the midterm, I was calling everybody. I was, I couldn't even think about anything else because, how that is. I mean, your life's changing for the next 2 years. So the next morning, I go to take that midterm, and I had 100% going in, and I flat out failed the midterm. I got an F. on it. And I went into the professor and I'm like, I explained to him what happened, and he's like, you should have studied. I'm like, well, I was hoping for a little bit of a break. I got no break. So I got an A on every other test. I aced the final, and I still ended up with a B for the class. And it really hurt. It hurt because I dominated differential equations, and I got a B because I got an F on the midterm. So hopefully you'll be a little bit better than me when that time comes. But anyway, but I like this chapter in the sense that it really kind of helps you know a little bit more about what's going on. But I will tell you this, is that the professor that I had, he was very much into computers and did a lot of stuff with computers and differential equations, and which I thought was pretty fascinating. And this is back in, the early 80s. So anyway, so the first section in chapter 9 is on solutions, slope fields, and Euler's method. And I know none of these things have you ever really, you know something about solutions, but you don't know what these things are talking about. All right, so what is a differential equation? Well, a differential equation, a first order differential equation is an equation of this form, where the derivative is a function of x or a function of both x and y. So if you can take the derivative and the derivative is a function, then the original equation is a differentiable, or it's able to be differentiated. You can take the derivative. Okay? So that's all it means. It just means you can take the derivative of this equation. All right? Now, so here this says, show that if y equals c divided by x plus 2, then the derivative is 1 over x times 2 minus y. See, that doesn't even seem to make sense, all right, when you look at it like that. But let's see if we can kind of make some sense of it. So here, this is saying that dy dx, if y equals c divided by x plus 2. All right, see that, think of that as c, and then this is x to the minus 1. Well, then the derivative of x to the minus 1 is negative x to the minus 2. So if y is equal to this, then the derivative dy dx is negative c over x squared. Just thinking of the x to the minus 2 going down to the denominator. And then the derivative of the constant is going to go away. All right? But now, this is not the same thing as that. So what we have to do is show that these two things are the same, that they're equal. All right? So we start off with 1 over x times 2 minus y. But see, then if the derivative is in terms of y, then we can replace y with what y is equal to. So 2 minus y, so I replace y with this, c over x plus 2. That was my original y. And so now if I simplify that, distribute the negative, well, now the 2's are going to cancel, and so I get 1 over x times negative c over x, and so I get negative c over x squared, which is what I got. Okay? All right. So I'm going to leave this up here. Oh, did you get the printout? I just sent it about a half hour ago. Did y'all get the guided notes for 9-1?
I didn't.
You did not?
Neither did I.
Okay, all right. Okay, so let's so let's go to the problem, man. Okay. All right, so we want to show that if y equals negative c over x plus 5, then dy dx equals 5 minus y divided by x. So see if you can do that. And when you write this down, I'll go back to the problem. Or maybe I can just tell you. So start off by taking the derivative of this, of what y is equal to. And then show that it's equal to this right here. All right, so Weston, let's start with you. If y equals negative c divided by x plus 5, then what is dy dx?
C over x squared.
C over x squared. Okay, everybody cool with that? All right. And so now if we take, so we're trying to show that this is equal to this. All right, so Tobias, how do we do that? How do we show that these two are equal to each other?
Would you plug? I don't really remember what we did, but I remember we plugged in C, right?
No.
You plug in. You plug in Y. That's what you plug in.
You plug in y. So you have 5 minus. So then in place of y, you plug in negative c divided by x plus 5. Divided by x. Okay. So is this going to be equal to c over x squared? That's what we're hoping to show. All right, so Tobias, when we simplify inside the parentheses, what do we get?
When you simplify inside the parentheses, you get 5 plus C over X minus 5. Then your 5's cancel out. It's a minus 5 after the C over X.
Oh, thank you. And so then you get c over x divided by x. And so then that's equal to c over x squared. Okay? So what we're just doing there is we're kind of proving that it's a differentiable equation, that it's a derivative, and then we can even say what the answer is. Okay? Now, let's all right, so a first order initial value differential equation must satisfy the particular solution. So we did those a lot in Calc 1, where basically it helps us figure out what the C is. Okay? So the particular solution helps us find C. So like if I say the f of 2 equals 3, or it contains the point 0.05, then that's a particular solution. And so we use that information to figure out what C is. Okay. All right. So we want to show that that y equals x plus 1 minus 1/3 e to the x is a solution to dy dx equals y minus x. And then this is our particular solution. The y of 0 equals 2/3. Now, that's the same thing as saying that it has the point 0 2/3. So the particular solution can be given either way. Okay? So the first thing we do is we take our initial function here and take the derivative of everything. Okay? So the derivative of y is 1 dy dx. The derivative of x is 1. The derivative of 1 is 0. The derivative of negative 1/3 e to the x is negative 1/3 e to the x. And so that simplifies to 1 minus 1/3 e to the x. So that's the derivative. So what we want to show is that 1 minus 1/3 e to the x is the same thing as y minus x. So just like we did in the last problem, we're going to substitute in for y what y is equal to up there. So we have x plus 1 minus 1/3 e to the x. So all that's y. And then minus x. We're hoping that that's equal to 1 minus 1/3 e to the x. So now when we simplify, we get the x's cancel. So we get 1 minus 1/3 e to the x equals 1 minus 1/3 e to the x. So we got it to work. Now, but there wasn't a c in this one. There wasn't a c in this one. So what we have to do then is we have to verify that 0 2/3 is actually on the curve, on the original curve. So my original function, I need to plug in 0 for x, 2/3 for y, and hopefully it'll work out. Okay? So there's my original function. I plug in 0 for x, 2/3 for y, and see if it works out. Well, let's see. E to the 0 is 1. 1 times 1/3 is 1/3. So I get 1 minus 1/3 is 2/3. So it works. So if when you plug in the point, if it's on the line, then it will satisfy it. Okay? So that 0 2/3 is an initial condition. And so we're showing that it is part of the original graph. Okay. All right. So let's try this one. So show that the function x squared plus y squared equals 16 is a solution to the first order initial value problem dy dx equals negative x divided by y, and that it satisfies this condition, that y of 0 equals 4. All right, so Jada, do you remember how to take the derivative of x squared plus y squared equals 16?
Would you use the power rule?
No, because, well, I guess in a way. So this is an implicit function, so it's not solved for y. So you just take the derivative of each part. So the derivative of x squared is what?
2x
And the derivative of y squared?
is 2y.
2y dy dx. You have to throw in the dy dx. And then the derivative of 16 is?
0.
0. Okay. Okay, so then when you solve that for dy dx, what do you get?
I got negative 2x over 2y.
Good. And then you can cancel the 2's and you get what?
Negative x over y.
Negative x over y. So that's what you wanted. That's what you wanted is negative x over y. And so then the last part is you have to show that this initial condition is on the original function. So the y of 0 is equal to 4. So you're going to plug in 0 for x, 4 for y, and see if it works. Okay, so there's your function. So you're going to plug in 0 for x, 4 for y, and it works. Okay? So it checks. So that is on the original curve. The 0.04 is on the original curve. It's actually circled. All right? Any questions on that? Okay. So we're going to do some more of that in the next section, but that's just kind of all there is on this in this section. So again, maybe after you take the midterm, because this is not going to be on the midterm, but it would be a good idea to practice some of these and just kind of get a feel for it. All right. Now, so the next idea is what's called a slope field. Okay. Viewing solution curves. Each time we specify an initial condition, the y of x sub 0 equals y sub 0, for the solution of a differential equation, y prime equals f of xy, the graph of the solution is required to pass through the point 0, y sub 0, and to have a slope y prime or m. So what this means is that every time we change the initial condition, or we change, it's like changing the y-intercept, we still have the same slope. And so if we just change that one point, then we're going to get a different line. It's just going to be moved up or down. So I don't know if it makes sense or not to you, but to me, these slope fields, it's kind of like learning more about the function by looking at the different slope fields. So all these different slopes. So to me, it's kind of like seeing through like a radar, like how a dolphin sends out radio waves or a bat, and then you see kind of how it bounces off. Looking at the slope fields, it's kind of like you're seeing the original function based on just the derivatives. Okay. So, All right, so let's look at this example here. So x squared plus y squared is 25. Again, this is implicit because it's not solved for y. You take the derivative, and just like the other ones, we get a slope of negative y over x. Okay? So what that means is if we pick values that are on that function, so if, okay, so like the 0.50, okay? Well, so 50, negative 5 over 0, that's undefined. So at the 0.50 is on the curve, all right, so 50, but the slope is undefined. It's a vertical line there. All right, if we look at the 0.05 that's on the curve, well, negative x over y, so that would be 0 over 5, so the slope would be 0. So if we graph the 0.05, then again, the tangent at that point would be 0. And so any point on the curve, we can figure out what the slope would be at that point. And then if we just add a constant, then we get a parallel line to it. Okay? All right? So let's look at the 0.34. Okay? Because, and again, where are these numbers coming from? Well, I'm like 3 squared plus 4 squared is 25. So I'm getting points that are on the curve. So if the derivative is negative x over y, the slope at that point would be negative 3/4. So I go back over here. So if this is the origin, then the 0.34 is going to be up here. So the slope is negative 3/4 at that point. So we can look at any point on the circle or add a constant to it, and we can figure out what the slope would be. And so if I took away the circle and looked at all the slopes, these slopes would kind of almost form a circle at the point. And I could know something about the original function just by looking at the slopes. Okay? All right. So, okay, so this says draw the slope field for dy dx equals 2. All right, so what does that even mean? Dy dx equals 2. What does that have to do with slope? How does dy dx relate to the slope?
It is the slope.
It is the slope, okay? So draw on your paper that all of the lines that have a slope of 2. And now they can differ by a constant, so you could have a constant, move it up or down. But so draw the lines that have a slope of 2. And we're just approximating. You don't have to measure it or anything. Okay? So think of the equations y equals 2x plus c. So you could have a different constant, but the slopes are going to go up 2 and over 1. So all of those parallel lines, that's like a slope field. Okay? Because they differ by a constant. We don't know what the constant is, but that's a slope field. Okay? So what you can do is you could actually calculate at any x and y what the slope is. Okay? All right. So let's see here. Okay, so these are some more complicated graphs with the slope field. But see, this is showing that like along here, that slope is going to be, let's say, up 1 over 1. So at that point, the slope is 1. But then if you look at another point, let's say at the point 2, 0, the slope is going to be like a negative, maybe a negative 1. Or at the point -4, 2, the slope is going to be very steep. So here, so these slopes, when they're changing like this, they're going to be like the one that's in terms of x and y. It's not going to be always the same, but it depends on at what point. See, here's the point 0, 2/3, and the slope is pretty close to 1. But then at the point maybe 1, 0 or 1, 1, the slope is about 0. And then it starts going down. And so you can kind of trace it along any of these paths. Or you could pick a point and calculate or approximate what the slope is anywhere in the slope field. Okay? Now, what's kind of cool is that there's some calculators now that will, I think the TI-89, that will actually graph slope fields, which is pretty amazing. Okay? But you can just use it to, so these little lines, they're just to approximate what the slope is at any point. Okay? So, you know how like you have different curves, that like you can trace different curves? So what would cause you to be on a different curve, a different path, is just the constant. So it's like the constant moves you from one slope path to another. And so then you can just kind of say, well, otherwise the point is that you change the points, it's just you're going to stay on one line. Okay. All right. So we'll talk a little bit more about slope fields, but that's pretty much it. I mean, just the idea to give you a visual of what a slope is. And so you got to remember, like, this is a positive slope, 0 slope. Vertical line is undefined. If it's going down, it's a negative slope. That's really all you need to know as far as that goes. Okay, so the last thing here is what's called Euler's method. And this is if you remember Newton's method, we used to approximate solutions. And we did it by what we call a recursive algorithm, where we use the last answer to get a better approximation of a 0. Well, now this is sort of like the differential equation version of Newton's method, and it's Euler's method. So again, it's used to approximate solutions. Okay? So what you do, let me make sure I've got all these, okay. So you start with your initial guess. We're going to call it y sub 0. All right. Then your next guess, your y sub 1, is your first guess plus the f of x sub 0, y sub 0. So you put that into your equation. And then you'll get your second approximation. Then you take that and then you plug it in and you say, then your second guess is your first, well, y sub 0, then y sub 1, plus the f of x sub 1, y sub 1. And then finally, we usually will do it 3 times. And that will be your second guess plus the f of x sub 2, y sub 2. Now, this is basically this is number crunching, okay? This is mostly stuff you just put in the calculator, all right? Okay, so let's, so it says find the first 3 approximations using Euler's method for, okay, so this is your derivative. Y prime equals 1 plus y. This is your initial condition, y sub 0 equals 1. Starting with x sub 0 equals 0. So that you have to be given where to start your guess. And then dx equals 0.1. So that's your, so you have your initial value right here. All right, so here's your given differential equation, okay? Your starting point, your change in x. All right, so, so your y sub 0 is equal to 1. So then your y1 is y sub 0 plus, and then the derivative at 0, 1 dx. Okay? So here's the derivative. So if we plug in, well, there's no x to plug in, but we plug in 1 for y. So we get 1 plus 1 right here times dx, 0.1. So we work that out. So that's 2 times 0.1 is 0.2 plus 1 is 1.2. So that's our y sub 1. Okay, so now let's go through this again. So our y sub 2 is, so the y sub 1 that we just got plus, now for the derivative, we're going to plug in x sub 1 and y sub 1 times dx. All right? Now, so our y sub 1 is 1.2 plus. All right, now, where does this 1 come from? Well, the x of 0 was 1, and then we're going up by 1 each time. Okay? So then the x of 1 is going to be 1. Y sub 1 was 1.2, and the dx is still 0.1. All right, so then that's 2.2 times 0.1. So we get 1.2 plus 0.22, so 1.42. All right, so what do you think y sub 3 will be? So if we set it up, so we'll get y sub 3 equals, what will come first?
The 1.42.
The 1.42. So y sub 2 plus the derivative at x2 and y2 dx. Okay, so we get 1.42 plus x2. Why did the x2 not go up? Oh, here we go. So y2 so let's see the y prime. Oh, Oh, because the derivative, it's always 1. It's where is it? It's 1 plus y. So the x isn't changing, it's always 1. But the y is going up. So it's 1 plus 1.42 times dx. And so then we end up with 1.662. Okay, so I know it's a little bit, at first it's a little tricky to know where to plug stuff in, but with a little bit of practice, you'll be okay. You'll actually like these, believe it or not. Okay, so let's do the one. At least let's start setting up the practice, because this is the last practice problem on the sheet. It says find the first 3 approximations using Euler's method for y prime equals 1 plus y. So the y of 0 is 1, starting with x of 0 equals 0 and dx equals 0.05. So that dx, you're going to have that in every problem. Okay? All right, so the first one, y sub 1, is y sub 0 plus the y prime of 0 times 0.05. So what do we plug in for the y of 0? Oh, wait, that should be x sub 2. Yeah, this should be x sub 1. Sorry about that. Okay, so we get 0 plus, so when we plug in let's see, so the y prime of x sub 0, y sub 0, it